All right, welcome back. You're, of course, listening to Basic Logic and Open Introduction. I'm Dr. Nick McGinnis. In the last video, we talked about sentential logic as a formal system, and I introduced several of the binary sentential connectives, and, or, if, and of course, the negation. There's one left, the biconditional. The biconditional is also sometimes called if and only if. That's because it's actually logically equivalent to if and only if, as you can see in sentence 1 there. Now, logical equivalence means, roughly, that the main logical operators have the same truth table. They're logically interchangeable, and they mean the same thing in the context of sentential logic. So here's the truth table. P if and only if Q. You'll notice that the value of the if and only if is true when the values of its inputs are the same. So we have true, 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 false, false, true, and false otherwise. In other words, the biconditional operates in such a fashion that if the values of its inputs are identical, it will output true. So in a way, it states that P is both a sufficient condition for Q and a necessary condition. Now, sufficient and necessary conditions is kind of part of the technical concepts of philosophy you might have bumped into already. Something's being a sufficient condition means it's enough to bring it about. A necessary condition means it needs to be present to bring it about. So, for example, a necessary condition for fire is the presence of an oxygen source. But air is not a sufficient condition for a fire. There's air where there's no fire. So, something being a necessary and sufficient condition means that the two are actually very closely related. Necessary and sufficient conditions often mean that they're in fact the same thing. So, they really kind of imply that the two things, P and Q, are the same. Roughly, but they're actually, it's a little bit more complicated than that. So the terms related in a biconditional, with the truth table we've just seen, don't have the exact same meanings, but despite not having the exact same meanings, they're logically interchangeable. For example, I could say something's a triangle if and only if it's a three-sided figure. Now, triangle and three-sided figure don't have the exact same meanings, but they are logically interchangeable. Now, this is not the kind of class where we're going to go very in-depth about the difference between meaning and reference, but lots of logicians have written about it. Frege and Russell, who are often kind of the first text you'll read in a philosophy of language class, do have a lot to say about the difference between sense and reference. This is not what we're going to be doing here. The idea is merely that when talking about the biconditional, what we're saying is that P if and only if Q means that for the purposes of SL, they're going to be interchangeable, because they are always going to have the same truth value. So the biconditional expresses logical equivalence. In ordinary language, necessary and sufficient conditions often mean we refer to the same thing. There's thunder if and only if there's lightning, but they're the same thing. For definitions, someone's a bachelor if and only if they're an unmarried male. However, in the context of our logic, the biconditional is actually going to prove pretty useful for testing various properties of sentences of SL, which is, of course, what we're slowly working towards. So those are all the sentential connectives we are going to be working with. Again, it's and, or, if. Negation, biconditional. And, or, if and only if, not. And as I warned earlier, don't try and think through these concepts using your ordinary logical intuitions. Don't stop and think, oh gosh, what do we mean by if? That's a mistake. The 5 operators and their truth tables are kind of stipulated. They're artifacts of the way we've set up our logical system. They're artifacts of the fact that we are dealing with bivalence, with atomic sentences representing statements. So you have to memorize these truth tables. You have to have them at your fingertips. And once you have them down, the next step is to be clear on the different ways you might need to use these connectives. For example, the conditional. When you're translating, as we will, from a natural language to sentential logic, you have to be clear on the distinction between if, only if, unless, and my tip here is to focus on when the conditional is falsified. So here are all the 5 truth tables. Again, how do the truth tables work? It's easy. Every component here has a truth value. The only component that doesn't have a truth value in sentential logic are the brackets, which are merely used to disambiguate complex sentences. So the atomic sentences, P and Q, which is kind of the traditional sentence letter, which could represent anything, People use P and Q for historical reasons. We're not going to get into it. But they have truth values. Those are the atomic sentences representing statements. And then the logical operators, the sentential connectives, the binary and unary connective not, have truth values as well. And their truth values are a function of the truth values of the things that connect it. So the and over here, for example, has a truth value of true when both of its inputs are true, and it's going to be false otherwise. You might be thinking, how do I know whether the inputs are in fact true? Well, that's going to be a function of the specific argument that you might be evaluating, the specific example we're using. The truth table is important because it gives you every possibility. So you know that an and is going to be false when either side of the things it's connecting are false. That's an abstract point. In a specific example, you might have to evaluate that for yourself. Here's the or, which is only false in one case when both sides are false, so it's an inclusive or. The conditional, which is only false with the antecedent, the P is true, but the consequent false. Why? Because it's saying something solely about the antecedent. If P then Q is a statement fundamentally about P, it's about what happens when P is true. So it's going to be falsified when P is true but Q is false. The biconditional is if and only if. It's logically equivalent to the statement P if Q and if Q then P. It's going to have a special technical role for verifying various properties of sentences, sets of sentences, and arguments. We're going to get to that. And finally, the negation, who's the only unary operator as opposed to binary operator. It doesn't connect two things. Instead, it flips the truth value of whatever it is operating on. All right, so again, memorize these. Sit down with a piece of paper, do them over and over again until you have them down and memorized. Now, as we saw in the last video, the disjunction, the or that we have, is an inclusive or. That means if both sides of the or are true, then the disjunction, the or itself, is true. But you can express exclusive or. It's very easy. You say P or Q and not both P and Q. And this main logical operator has the truth table we'd expect. Going down from the top, it's false, true, true, false, i.e., when is it false? When both sides are true. That's exactly the truth table we'd want to see if we wanted exclusive or. Now, more generally, there are 16 truth tables that are possible given binary connectives and negation. If you think about it, the four rows over here only have 16 combinatorial possibilities. Right? They could be true, 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 false, 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 true, 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 false, and so on. If you go through all the possibilities, there are 16 total truth tables. Now we've chosen 4 of these plus negation to represent the sentential connectives we're interested in, which is and, or, if and only if. Why those 4? Well, partially that's a function of the fact that this is a philosophical logic class, and logicians have selected those 4 because they most closely represent logical concepts that we use in ordinary language. The truth table for P and Q, which is actually the subtable, this column right here, is actually pretty close to what we mean by and in most contexts. Sure, we lose a little bit of the semantics of a word like but or although. On the other hand, choosing this truth table actually has this useful function that if we're going to be evaluating the logic of an argument, the truth table for and is pretty close to our ordinary language and. But what about all the other possible truth tables? Well, the good news is all of them can be represented using a combination of the operators we have. Or you can also stipulate an operator. You can create one. You can use the symbol I have here, and then I could just say P exclusive or Q, and it'll have this truth table. So in a way, it is kind of arbitrary which binary truth tables we assign as the primary logical operators or sentential connectives in our formal system. The important thing is we're able to express all 16 possibilities using the connectives we have chosen. If you're taking a computer science course, for example, the 4 sentential connectives that we traditionally use in a philosophical logic class are going to be less important. For computer science, you might be interested in a NAND gate or a XOR gate. What are important about these some gates is that some operators is that using only one, you're able to express the other 15. So here's a slightly more advanced exercise if you feel ready. So try to make a list of all possible 16 binary truth functions. Identify which ones are expressed by the 4 binary operators we already have, and, if, or, not, and, if, for, if, and only if. So, and we already know how to make the table for exclusive or using some operators, our 4 operators plus negation. So choose one of the remaining tables and try to do that the same thing. Try to express one of the tables that isn't expressed using the operators we have plus negation. One of the interesting facts, too, is that it's actually impossible to express all 16 using only and. So the really advanced question might be explaining why. So it's actually possible to express all 16 possible truth tables using 2 operators, and not. But boy, does it look complicated. But as I was saying, computers don't really care. They can use only one type, NAND and NOR, to generate all 16 possible functions, which makes them particularly important for circuit designers. So if you want to go down that rabbit hole, you certainly can. I've spent a lovely afternoon showing how to create all possible truth functions using NAND. Lots of fun. Okay, so we're going to pause the video, think about these questions, see if you can answer them. Did you pause? You didn't do it, did you? That's fine. We're moving on to more about sentential logic. So actually I have a solution slide here. These are all the 16 possible truth functions. So you could pause the video here and have a look at these. You'll see that the ones that we already have is or, if then, and, if and only if. And these are some of the NAND gate is particularly important for circuit designers. And so is NOR. You'll see that they're actually kind of the opposite of each other. Okay. Now here's another slightly less complicated assignment, which is to translate from sentential logic and to sentential logic from English as a natural language system. What we're going to do here is I have a key where the letters A, B, and C represent different statements, like Albert jogs regularly, Bob jogs regularly, and Carol jogs regularly. So Bob and Carol jog regularly, for example, would be B and C. Answer A, B, Bob, and Carol. So why don't we pause the video? You can work on these and then come back and see if you have the right answers. It's the awkward part. I just kind of wait. No, you need to pause. Did you do it? Is this screen is that visible? Okay. Bob and Carol jog regularly. Have you done them all? Awesome. Bob does not jog regularly, but Carol does. So it is not B, right? It is not the case that Bob jogs regularly, but Carol does. But, of course, is an and, so B and C. Neither Bob nor Carol jogs regularly. The neither nor can be expressed in 2 ways. It could be a negated disjunction or a conjunction, an and, where both conjuncts are themselves negated. Why do we do it the disjunctive way? So answer C would be, it is not the case that, where is it, Bob or Carol jogs regularly. Now here we have our first unless. Bob doesn't jog regularly unless Carol does. Remember how to do an unless? You can skip back a few slides. We talked about it. Roughly, the unless specifies a condition that something won't happen unless something else happens. So Bob doesn't jog unless Carol does. So what are some ways we can represent that? There's a couple of different options. So Bob does not jog regularly unless Carol jogs. So we know that we're going to have a few elements here, right? For example, it is not the case that Bob jogs regularly. So we're going to have not B, but unless Carol does. So one way we can represent it is, if Carol doesn't jog, then Bob doesn't jog. So if not Carol jogging, then not Bob jogging. That kind of captures the meaning of the unless. Because of course, think about the falsification condition for an unless. When is that statement not true? Bob doesn't jog unless Carol does. Well, the falsification condition would be if we see Bob without Carol. Is this falsification condition captured here? Well, let's put a big F under the if, and we know that would mean that this, the antecedent would be true and the consequent would be false. So it's false when it's true that Carol doesn't jog, but it's false that Bob is not jogging. Which of course is exactly the falsification condition we want. When is the statement false? When it's true that Carol does not jog. This T is pointing to the not, and it's false that Bob doesn't jog. Let me full screen the window here, just so we can see it better. Right? So, if not C, then not B. Right? If it is not the case that Carol jogs, then it's not the case that Bob jogs. Now, there are different logical equivalencies that you can substitute here. For example, I'm going to use the if and only if statement. This is actually logically equivalent to just kind of a flipped version over here. If Bob jogs, then Carol jogs. Why is that logically equivalent? Well, if you think about it, it's expressing the same thing, because if I see Bob jogging, then I can expect to see Carol jogging, because Bob doesn't jog unless Carol jogs. So both of these are good answers. All right. Albert and Bob and Carol do not jog regularly, so that's A, not A, and not B, and not C. And put a bracket somewhere. That's pretty easy. Although Carol does not jog, either Bob or Albert does. So you could say not C, and either B or A. Would you like to see that one? Why don't we do that? So let's erase these. So, although Carol does not jog, either Bob or Albert does. So what we're expressing here is it is not the case that C and parenthesis either B or A. The parenthesis is important because you want to make sure you express the right sentence. Look at that little mouse cursor. Is it? Didn't work. If Albert jogs, then Carol jogs. And if Carol jogs, then Bob jogs. All right. So what is that going to look like? So if Albert, then Carol, and if Carol, then Bob. What's the brackets here? What's the main logical operator? Looks like the and. Let's full screen it. So if A, then C, and if C, then B. And this kind of looks like a transitive property, which we can prove some stuff about later. Carol jogs only if Bob jogs. Here we have the only if statement. Do you remember how to do that one? Carol jogs only if Bob jogs, so the only condition where Carol will jog is if Bob jogs. So if we see Carol jogging, we know that Bob is out there somewhere. So if C, then B. Carol jogs only if Bob jogs, so the only condition where we can see Carol is if Bob's there. So seeing Carol implies we see Bob. That's the only if. Perfect. All right. Now we have some translations from sentential logic to English. Those are pretty easy, and you should do them yourself. This video is getting a bit long, so let's just do a couple of the easy ones. Then you should pause the video, do them by yourself. So, A and B, Albert and Bob jogs. Neither A nor C, it is neither Albert nor Carol jog. Not B, it is not the case that Bob doesn't jog. All right, you get the hang of it. Do them all, and we're going to come back in just a sec. All right, good job doing all those things. I'm sure you did. All right, now the next thing we're going to talk about is something a little bit more complicated. Now, a lot of logic classes actually start with the syntax of SL. I didn't want to do it that way. I wanted to just throw you right into kind of playing the game of SL. Whenever I sit down with some friends and I introduce them to a new board game, going over the rules is kind of less worthwhile sometimes than just setting up the board and then just playing and learning as we go along. And that's what I thought we should do here. So now that we have some extra practice exercises under our belt and we all know all the truth tables, we can actually formally define the syntax of sentential logic as a formal system. What is a syntax? Well, it's a set of rules that govern the generation of sentences in a language. In other words, it will define what counts as a sentence and what doesn't. We can put together the symbols of SL in ways that don't actually make any sense. Remember, we have sentence letters, connectives, and parentheses and brackets. Now, a sentence like bracket, bracket, P, Q, and bracket is just a meaningless string of symbols because it's not arranged according to a syntax or a grammar. The syntax of SL has an interesting property that Aristotle's formal system didn't have. It's recursive. The rules can be applied back to the output of the rules indefinitely. This is a bit like the rules of the MIU puzzle from a few videos ago. Those were also recursive, i.e. the output can be reapplied as an input to the rules. In order to give a recursive syntax, I have to introduce another technical concept, a metavariable. Now, the sentence letters are variables that stand in for statements. So we can translate them back and forth in specific contexts, but when I give you, for example, a truth table with the standard sentence letters P and Q, they're standing in for any statement. Now, metavariables themselves are one higher level of abstraction. They can stand in for any full sentence of SL that's well formed. So the metavariables, I'm going to be using uppercase bolded italic letters. So if I have the sentence of SL A and B, and that's a sentence, right, in good standing, I can represent that by the metavariable P. Why is this important? Well, because using a metavariable will allow me to create a recursive set of sentences, a recursive set of rules to generate new sentences that will then allow me to stipulate how we can shape infinitely many sentences of SL using finite means. With just a few rules, I can define the grammar of sentential logic in such a way that we will be able to have infinitely many sentences. That's pretty cool. How does it work? Well, first I say, well, any atomic sentence is a sentence of SL. What's an atomic sentence? Your regular, right, uppercase letters, not bolded, just like A or B, Albert jogs, Bob jogs. Then I say, well, look, if A is a sentence of SL, then not A is a sentence of SL. And here the idea is pretty straightforward. For any sentence that I generate using these rules, if that's a sentence, then some other syntactical construction I also stipulate to be a sentence. So if A, whatever A could be, is a sentence, then not A is a sentence. So suppose I start with an atomic sentence. Suppose that's, we'll choose a random letter. How about F? So if F, represented by the metavariable A, is a sentence of SL, then not F is a sentence of SL. But if not F is a sentence, then not F is a sentence, because not F becomes the new sentence of SL that could be re-inputted to rule number 2. Likewise, look at rule number 3. If A and B as metavariables, standing in for any sentence of SL in good standing, if A and B are sentences, then A conjunction, A and B, are sentences of SL. A conjunction B is a sentence. So for any two sentences of SL, then A and B is a sentence itself of SL. Remember, the bolded uppercase letters, such as A, are metavariables. The idea is here we can represent any full grammatical statement of sentential logic. Every atomic sentence is a sentence of SL. So if I say P is a sentence, then not P is a sentence, not P is a sentence, so on and so forth. P and P is a sentence. P and P and P and P is a sentence, right? Using these recursive rules, the output of the rules becomes the input, and then I can just iterate this process to generate arbitrary long sentences. So here it is, 7 rules. The formal language of sentential logic, the syntax, is defined entirely by these rules. If a string of symbols cannot be generated, it is not a sentence of SL. And if something is not a sentence of SL, it cannot be generated by these rules. So notice that these are kind of like, these are opposite statements. These are kind of contrapositive statements, right? If a string can't be generated, it's not a sentence. And if something is not a sentence, it can't be generated. So it covers both bases. So there's no sentences, for example, that should be syntactical but can't be generated. And if something can be generated, it's not syntactical, so these sets overlap perfectly. So let's do a couple of examples here, just to make sure we understand this abstract notion of a recursive syntax. All right. So every atomic sentence is a sentence of SL. Let's choose an atomic sentence like, I don't know, P. So this is a sentence of SL. If P is a sentence of SL, not P is a sentence by rule 2. If not P is a sentence of SL, then not P and not P is a sentence, right? Because now this becomes the whole meta variable, the complex statement that I could add information to. So if not P, let me just erase this parenthesis. If not P and not P is a sentence of SL, then I can also make a big bracket here and say negation. Right? Because now this whole sentence can be negated using the rules, right? Because if this is a sentence of SL, then negation this is a sentence of SL. So it's not the case that not P and not P. And that's a perfectly cromulent sentence. And could I continue iterating this process? Sure. What are the stock of sentences I've already created? Well, I have not P here, so I can go, of course, like this. Every sentence letter is also a sentence. So I can introduce things, right? I can go, well, Q is a sentence, so not P or Q is a sentence, right? These are all valid sentences that can be created using the recursive rules. Now, is this concept of recursion going to prove really crucial to proving formal properties of SL? Not at this stage. When we get into some of the meta theory of logic, where we're proving properties of the system itself, we're going to circle back to this notion of a recursive syntax, because the notion of what we call mathematical induction, to prove things like the consistency or completeness of sentential logic, how we define the syntax will actually matter. For now, I wanted to introduce the concept of recursion in order to give you the full grammar / syntax of sentential logic. Now, one more small thing. If I have a sentence such as P, Q, and bracket, bracket, or S, is that a sentence of sentential logic? Well, no. It's obviously meaningless. The binary connectives aren't connecting anything. You have 2 sentence letters next to each other. It doesn't have a meaning. If I say P and Q, it's pretty clear that I mean P is Q and Q is true. This doesn't have a clear meaning, in part because it's not syntactical. There's also no way to generate this sentence using the recursive rules that we have. If you tried to use the rules to generate this, you wouldn't get even close. At best, you might get something, the closest you might get would be P and Q or S. That's a grammatical sentence, but this one isn't. And interestingly enough, the recursive syntax of SL allows you to generate all and only grammatical sentences of SL. SL being sentential logic. Now, I just want to reiterate again that the binary connectives are binary at every level. According to the rules, they always connect 2 chunks without ambiguity. So, for example, you see sentence 1 here is not a real sentence because it's ambiguous. But sentence 2 with brackets showing that the and is connecting 2 chunks, A and what? B and C. That's grammatical. It can be generated by the syntax of SL. 3 is also ambiguous. Here, and 4 and 5 represent 2 other possible interpretations of 3. Is it A and B, or C? Or is it A and B, or C? So the string of symbols given in 1 and 3 are not genuine sentences of sentential logic because they violate the syntax, and it's impossible to give them a truth table. All right, a couple more concepts here. I know this video is getting a bit long. Now, there always is going to be a main logical operator. I've talked a little bit about the main logical operator already. The main logical operator is roughly the last one to take its truth values because its truth value is a function of all the truth values that come before it. And since the binary connectors are binary and always connecting to chunks, the main logical operator is the highest one that connects the two largest scale chunks of your sentence. Negation is slightly different. It's not a binary connective. It operates instead on one connective at a time, or one atomic sentence, the next one in line, as it were. So let's look at these 5 sentences here. The main logical operator in sentence 1 is the if-then. Why? Because it connects if this whole long thing here to then this whole long thing here. If-then. Second sentence, the main logical operator is the and, not P and neither Q nor R. Sentence 3 is similar to 2, but notice where the brackets are. The brackets separate out the not from the P. So it is not the case that what? It is not the case that P and neither Q nor R. So take a few minutes to really look at how sentence 2 and 3 are syntactically different because of the brackets. Not P and, it is not the case that P and neither Q nor R. In sentence 4, the main logical operator is the or, either not P or Q, whereas in sentence 5, the main logical operator is the negation, because it applies to the disjunction, the or. It is not the case that P or Q. The brackets tell us what we call the scope of the negation, whether it operates on the atomic sentence, as in sentence 4, not P or Q, or if it's operating on something else, the longer sentence in parentheses, in which case, in sentence 5, for example, it's operating on the or, on the disjunction. It is not the case that either P or Q. So, why don't you take a few seconds and work out those truth tables. Maybe just for 4 and 5, because they're pretty long truth tables otherwise. All right. Now, if you want to get really technical about it, A and B by itself is not a sentence. It needs the brackets. But for convenience, we're going to drop parentheses where they're not required to reduce ambiguity. But it doesn't change the framework of the recursive syntax. It just makes it easier for us to read SL. The book For All X, which is kind of the basis for this course, which you should be reading along in, we're still in chapter 6, sometimes says it suggests that when order really doesn't matter, like on the and, where brackets can't possibly change the meaning, you don't need to use them, but I think that's a really bad habit to adopt. I think you shouldn't do it whenever you have possibility of ambiguity. Just use the parentheses. That's my advice to you. All right. Now, the practice exercise for this section would be E, F, G, and H from 6.4. Now, we're not going to go over these together. I want you to stop the video at this point and do the exercises. All right. So again, that's in For All X, the Lorain County remix, section 6.4, parts E, F, G, and H. All right. Have you done them? Good. We're going to stop the video now. We're at 34 minutes, and we're going to pick them up in the next video. Thanks for listening.